Now that we have some tools to understand minimums and maximums, both local and absolute, we can come back to the real reason that we were talking about minimums and maximums, which is the fact that they come up a lot in applications. Often in applications, you want to find when something is biggest or smallest or highest or lowest or hottest or coolest, some sort of extreme value. And in those situations, usually, once you sort of phrase things mathematically, you'll be looking for the minimum or maximum of some function. So in these sorts of situations, when you're looking for some kind of largest or smallest or whatever, usually the things that you'll do to solve that problem is first express the thing that you want to find the largest or smallest for as a function of some variable that you can either control or understand, some kind of input variable. Once you have that thing expressed as a function of some input variable, then you'll try to understand some domain for the function. And sometimes the domain will come from the function itself, but often the domain will come from the situation. Like in many situations, some input values just won't make realistic sense. So for example, if a distance is your input value, then it doesn't make sense for it to be negative much of the time, because if you're talking about just a distance as opposed to a displacement, it can't be negative. Once you have a function that you want to find the minimum or maximum for, and you have a domain, well then you can go ahead and find the absolute minimum or maximum of that function, depending on what you're looking for, a smallest value or a largest value. And once you've done that, you do need to be careful when you're answering the actual question that was asked, whether you want to provide the input value that produces the maximum or minimum, or the output value that is the minimum or maximum output. Because sometimes you just want to know what the maximum is, and sometimes you want to know where it is. So that's the distinction between output and input. Let's look at how this works in practice in one example. So for example, suppose that we want to find the dimensions of a rectangle with maximum area whose perimeter is 10 centimeters. Now, you might sort of have an intuitive idea of what the answer to this sort of question is. I think it sort of makes intuitive sense that just kind of by symmetry, if you have a fixed perimeter, then the rectangle with maximum area ought to be a square. So we kind of expect to find that the dimensions of this rectangle should be a square. But let's go ahead and see if this process actually produces a square as the result. So express the thing as a function of some variable that we control. Well, we're looking for rectangles, and rectangles have a height, let's call it y, and a width, let's call it x. And the area is the thing that we want to maximize, and that's just x times y. Now this is something that often happens in these situations where you have too many variables. To take a derivative and use this maximum finding process that we've come up with, we need to really have our function be a function of one input variable. And here we have two variables. When this happens, there's usually a relationship between the two input variables that's somehow hidden, and often it's hidden in the problem somehow. You might notice that in this description of the problem, we actually haven't used the fact that the perimeter has to be 10 centimeters. So what is the perimeter of a rectangle? Well, if the rectangle has width x and height y, then the perimeter is twice x plus twice y, because there's x here, and there's also x across the top, and then there's y on that side, but also y on this side over here. So 2x plus 2y. But the perimeter has to be 10 centimeters, so the perimeter is actually 10. So 10 equals 2x plus 2y. And you can see we can use this extra relationship to eliminate one of the two variables, x or y. It's really our choice which one we want to eliminate. Let's eliminate y, I guess. So we can solve this equation for y. We get y, let's see, move 2x over, divide everything by 2. You get y is 5 minus x. And then we can put that into our area formula to make it a function only of x. So now we have area as a function of x, and it is x times 5 minus x, or 5x minus x squared. Now, this particular function that we want to find a maximum for is quadratic, and we know where quadratics that open down have their maximum. They have their maximum at the vertex, but let's use these calculus tricks just to see how they work. So find a domain for this function that makes sense in our situation. So how small does it make sense to let this variable x get? Well, x is a length, and it doesn't make sense for it to be negative, right? What would it mean for a rectangle to have negative width? That just doesn't make any sense. So x has to be greater than or equal to 0. But if x gets bigger than 5, then there's no perimeter left for a height, right? Because if x is 5, then you have 5 across the bottom, 5 across the top, and you've already used up all 10 of your perimeter that we're allowed to have, and so there'd be nothing left for y, and so x has to be less than or equal to 5. So here's the domain that makes sense. Now, in this case, we have a bounded and closed interval for our domain, and the function that we're trying to find the maximum for is continuous because it's a polynomial. So we have a continuous function on a closed and bounded interval. So we know from the extreme value theorem, we know ahead of time that there is a maximum value. So now we can just use our calculus tricks to find that maximum value. So now that we know there is an absolute maximum somewhere, we can go ahead and find it. We know because of the extreme value theorem, because we have a continuous function on a closed and bounded interval, we know that the maximum happens either at an endpoint or at a critical point. So the endpoints are 0 and 5. Now let's find critical points. So we need to take a derivative of the function we're trying to maximize, and the derivative is 5 minus 2x. This derivative is defined everywhere, so we don't get any critical points coming from places where the derivative is undefined. So we only have to worry about places where the derivative is 0. So set this equal to 0 and solve, and you get x is 5 halves. And so our other possible maximum is at 5 halves. Now that we have all of the possible candidates where a maximum might be hiding, we can just plug them into the original area function to see which one gives us the biggest. So when you plug in 0, the area function gives you 0, right? Remember, area function is up here. When you plug in 5, you get 25 minus 25, 0 again. And so the maximum had better be at 5 halves, which is not really a surprise given the fact that this was a quadratic. So 5 times 5 halves minus 5 halves squared. So this is 25 halves minus 25 quarters, and that's 25 over 4. So 25 over 4. And because we're dealing with a distance, it probably makes sense to express this as a mixed number, I would say. So this is, 6 1/4. And this is centimeters. Square centimeters, sorry, because this is an area, right? This 5 1/2, this is 5 halves, this is 2 1/2 centimeters. Okay, so now we have an x value that produces the maximum output. So the x value that produces the maximum area is 2 1/2 centimeters. The actual maximum area is 6 1/4 square centimeters. So let's be careful about actually answering the question. Remember, the original question was, what are the dimensions of the rectangle that has the maximum area? So we named our dimensions x and y. We know that to get the maximum area, x has to be 2 1/2 centimeters. We should find y, right? To completely answer the question, we should say what the width and length of this rectangle has to be. So, but remember, y was 5 minus x. That was one of this extra relationship that we found way up here. So y is 5 minus x. We found that the x value we want is 5 halves, and 5 minus 5 halves is 5 halves, which is 2 1/2. And so the y value that produces the maximum area is 2 1/2 centimeters. And so, sure enough, as we suspected, the rectangle with maximum area that has the given perimeter of 10 centimeters is the square that's 2.5 centimeters on each side. So you can see that this process, we did get a little lucky in that the domain we happened to come up with was a closed and bounded interval, and the function was continuous, so we knew ahead of time that we were guaranteed to have a maximum value. But other than that, this process would work in a lot of different situations. Really, the tricky part isn't the calculus, which is down here. The tricky part is coming up with an appropriate function that describes the situation that you're dealing with.